Hi there and welcome to my channel. In this video, I'll be discussing the concept of normalization of wave function. If you're an undergraduate student or you're interested in quantum physics, I'm sure you find this video interesting. We'll start by examining the normalization condition and then we'll solve 3 examples involving normalization of wave functions. If we recall one of the postulates of quantum physics, that is, the state of a particle is specified by the wave function being a complex function of position and time. And then if we use wave functions rather than positions, we are actually representing a clean break between classical and modern physics. The wave function is the description of the quantum state of a system. A particle has to be found somewhere. The probability that a particle must be found somewhere is 1. That is 100%. And this idea is what we use and we call the normalization condition. That is, if we integrate the wave function, the square of the wave function from -infinity to infinity with respect to x, it should be equal to 1. If a measurement is made at a time t to locate a particle associated with a wave function, the probability that the particle is found in the region, let's say x1 and x2, is equal to the square of the wave function. And this is Max Born's postulate. Now let's consider some examples. You have the wave function psi is equals to a to the power a exponential minus alpha x. And we want to normalize and then get a from by normalization. Now we already have an expression of the wave function. So what we need to do is consider the normalization condition, that is from -infinity to infinity of the square of the wave function with respect to x is equal to 1. If the wave function doesn't have a complex number I, the complex conjugate of the wave function, that's phi star, must be equal to the wave function. So now we just put this wave function into the normalization condition and then we solve for a. Now, x can be negative or it can be positive. So with that information, we can actually split the integral from -infinity to 0, which takes care of all negative values of x, and then from 0 to infinity and takes care of the positive value of x. This is to help simplify the problem. Every factor that is independent of x is factored out from the integral. Like you have a squared being factored out in this case. Then we take the integral, a bit of calculus integration here would be useful. We integrate e to the power of 2 alpha x, and then we're going to have this expression as it is here. Now, at the end of the day, we'll be having 1 over 2 alpha common to both terms here, and so we can factor it out. So we have a to the power of 2 over 2 alpha, and then we have e to the power of 0 minus e to the power of -infinity, and then this, having applied the limit, of course, then you have e to the power of -infinity minus e to the power of 0, and then when we do this, what we have in the bracket should be equal to 2. 2 cancels 2, and then we have an expression for a, which is equal to the square root of alpha. So the normalized wave function is psi is equal to the square root of alpha, e to the power of minus alpha x. We have another wave function here, and then we also consider the normalization, the condition. In this wave function, we don't have a complex number, so psi star is same thing as psi, and then we put this into the normalization condition to get, to check if this integration will give us 1. Again, x can take negative values and positive values. So we can split the integral for simplification. So we have minus infinity to infinity that takes care of all negative values of x, and then 0 to infinity that takes care of positive values of x. If you do this carefully and follow the solution from top to the bottom, we're going to find this expression. One thing to note here is that E is a constant, and the value of E is named after Euler. A bit of mathematics here. E to the power of infinity is infinity, and E to the power of minus infinity is 0. Now, if you have a function e to the power of x, as x grows larger, the function becomes very large. But when x becomes small and even more negative, the value of the function becomes close or even closer to 0. So you have here that 1 over 2, then you have in the square bracket infinity minus 1 plus infinity minus 1 in another bracket. Infinity is not a number. You can't add to it. You can't subtract from it. So the solution of the bracket is indefinite. And what that means is that the integration from minus infinity to infinity of psi star times phi with respect to x is not equal to 1. And so we can conclude that the wave function is not normalized. You have a third function, a sine n phi over ax, describing a particle that is trapped in a well, or like in a region between 0 and a. Now, the potential outside this region is 0, so it means that the wave function doesn't have a value outside this region. Now, we want to find the constant a, and then we will need to normalize the wave function. Again, we start with the normalization condition. We put in the values of our wave function. There is no I, complex number, in this wave function. So the complex conjugate of the wave function is the same as the wave function itself. Put it in the normalization condition, and this should be equal to 1. Now, at this point, we'll be having sine squared n pi over ax dx. So we need to use some trigonometry identity here. Now, also consider we are taking the integral from minus infinity to infinity, but then we know that the wave function has no value in the region outside 0 and a. So the first integral here goes to 0. The third integral goes to 0. We can only have values for integral between 0 and a. So now we put this, and then we use our trigonometric identity that cos 2x is equal to 1 over 2 sine square x. We make sine square the subject formula, and then substitute it into equation star as it is on the screen. When we make this substitution, we'll find out that 1 over 2 is being present here and is independent of x, so we can factor it out, and then you have 8 squared over 2, the integral from 0 to a, and then you have this expression. A bit of calculus here, how to integrate your sine and cosine. And when you do this, we're going to have this expression. Something to also note, sine 0 is 0, sine pi is 0, sine n pi is 0, multiples of pi, then also 2n pi is also 0. So it means that this term here is going to be going to 0. This term also would go to 0, and you're just left with just one term, which is a. So finally, we're going to be having a to the power of 2 over 2 times a, and this should be equal to 1. And with that, we can find an expression for a, and then we can write the normalized wave function as psi of x is equal to the square root of 2 over a sine n pi over a x. I hope you find this video useful. Please like and subscribe. Thank you for listening and look out for my next video.